My name is Madison Blanton, and I'm a senior at Milligan University. Today, I would like to share with you all a little bit about my undergraduate research project, which is the creation of unnatural dipeptide antibiotics against Pseudomonas aeruginosa. I'd like to begin by giving you all a little bit of background information about cystic fibrosis. So cystic fibrosis is a homozygous recessive genetic disorder, which means that those who have cystic fibrosis must inherit this gene from both their mother and their father. Cystic fibrosis patients have a faulty cystic fibrosis transmembrane conductance regulated protein, and this protein is responsible for the movement of chloride ions from one side of the cell membrane to the other. When a CFTR protein does not work efficiently, there is a mucus buildup that occurs on the outside of the cell membrane. This mucus layer is a perfect breeding ground for the bacterial infection of Pseudomonas aeruginosa. So I want to explain to you all a little bit about how we synthesize our compounds. So we first make an F-MOC glide wang resin that will bind to the silica plate on the billboard shown on the left side of your screen. From there, we are able to go through an acylating process, which will add various halogens to the silica plate. Next, we will go through a hydrolysis process, which will protect the acylating agent as we then proceed through the alkylation process. So the alkylation process will allow us to bind various amino acids to create the dipeptide compound. From them, we are able to go through a cleavage mechanism, which will release the dipeptide compound that we have created into the collection vials shown on your screen. We're able to take the compounds and put them through a filtration mechanism as this HyperSep funnel, which practices size exclusion, which allows us to purify our compounds. We will take our purified as well as our crude compounds and put them in a biofilm assay and test them directly in comparison to known antibiotics that we have today for the Pseudomonas aeruginosa bacterial infections and see how well the dipeptides that we have created will combat Pseudomonas aeruginosa. We're able to determine this by doing a crystal violet analysis, and the concentration of crystal violet at the end will allow us to be able to calculate the percent of Pseudomonas aeruginosa that was killed by our antibiotics. So on the screen, I have a couple of the graphs from my results. So figure 1 is using the 2-fluoroacylating agent. Figure 2 is the 3-fluoroacylating agent, and figure 3 is the 4-fluoroacylating agent. These graphs also show the comparison of the pure versus crude compounds and their effectiveness of killing the Pseudomonas aeruginosa biofilm. Thus far, we have not really seen a huge difference in the evaluation of crude and pure product. However, this process can be improved by trying different filtration methods other than size exclusion. Also, in my research, I have found that the methionine amino acid is the best alkylating agent that we have identified thus far in combating the Pseudomonas aeruginosa biofilm. So I'd just like to thank you all for sitting and listening to a little bit about my undergraduate research project. If you all are still interested or have any questions for me, please feel free to join my meeting room, and I would love to talk to you all a little bit about my undergraduate research project. So thanks.